Okay, we're back with another how-to video. This time, I got a request for Giancali on page 163, number 37. So we're going to take a look here. As you can see by my excellent drawing, the situation here is we have a trampoline artist who is jumping from a box of some kind, landing on a trampoline, and then eventually depressing that trampoline. The height that he or she is jumping from is 3 meters above the surface of the trampoline. So that's the basic information we're given. We are also told that this person jumps with this speed, and then we are asked what is their speed when they get to the surface of the trampoline. Now, there's a couple ways you could do this. You could do this kinematics, or since we're talking about conservation of energy, you can apply the law of conservation of energy. First thing I'm going to do, as I suggested in class today, is I'm going to put together a force summation. By the way, for ease of communication, basically what I did is I called the point where they jumped off the box, I'm going to call that point 1. Point 2 would be when they land on when they first get to the trampoline, and then point 3 would be that position after the trampoline has been stretched or displaced. So with all that in mind, I'm going to start my energy summation, accounting for all the types of energy I'm dealing with here. So I just start that with listing all of the energy I could possibly have, and that is at point 1, and we are being asked to compare that point to what is going on at point 2. Okay, gravitational potential and the spring energy there. Now I go about eliminating the types of energy I don't have to deal with. All right. First of all, I take a look at the situation at the top of the box. Is there movement occurring at point 1? The answer is yes, so I keep that. All right. Does the person have gravitational potential energy at point 1? Yes, so I'm keeping that. Is there anything involving a spring or elastic energy of any kind? No, so I can eliminate that. And remember, now we're talking about point 2 when they first get to the trampoline before it's been displaced. Is there any kinetic energy? Yes, so I'm going to keep that. Is there any potential energy at this point? For our purposes at this point, we're going to go ahead and call this the frame of reference, so we're going to call that 0. So I'm going to say no. And then is there any type of potential spring energy involved? At this point, the trampoline hasn't been displaced, so the answer is no. So what do I do with this information? Well, this gives me a place to start with my conservation of energy expression. And so I know that that person has kinetic energy and gravitational potential energy at point 1, and whatever energy they start with at point 1 is going to equal the kinetic energy that they have at point 2 right when they get to the level of the trampoline. Now I can go ahead and expand that expression a little bit. So I know that the equation for kinetic energy is mv squared over 2, and that's at point 1. I know that the expression for potential energy is mg and then whatever that y position is at point 1, and that's going to be equal to, all of that energy is going to transfer or change into potential energy. It's going to change into, good thing I used a pencil, kinetic energy at point 2. All right, next steps is time to start simplifying here. I see that I have a term that will cancel out of each of those, so that simplifies it a little bit, and I'm trying to find this speed here. Something else I can do to simplify is I can just multiply both sides of that equation by 2, and that'll take care of these fractions that a number of you don't like. And so when I do that, I end up with, let's see, v1 squared plus 2gy1 is equal to the speed at point 2 squared. And then since we are solving for this, the speed at point 2 is going to be equal to whatever is on the other side. Of course, under the square root sign, speed at 1 and the position at 0.1. All right, from there, simple plug and chug. By the way, I'd like to point out here, notice that expression. You may recognize that from earlier in our kinematics unit. I believe there, the way it was written was, final velocity squared is equal to the initial velocity squared plus 2 times acceleration times whatever the displacement is. In this case, I mean there, I think they listed it as x, but in this case we're displacing in the y direction. Notice the similarity. That's not an accident. All right? That's why I said you could either approach this part of the problem by kinematics, or you could use it, you could approach it from a conservation of energy standpoint. All right, then the question is asked, if it behaves like a spring, and that spring just happens to have a spring constant of 6.2 times 10 to the 4th Newton meters, it wants to know how far it will get depressed. All right, how far out of from equilibrium will that trampoline get displaced? So now we're talking about 0.3. So I go back to my energy summation. Only now I'm going to be comparing 0.2 to 0.3. So the possible energies are kinetic energy, gravitational energy at 0.2, spring energy at 0.2. All right, and law of conservation says that whatever energy the system has there, it still has to have at 0.3. So the kinetic energy at 0.3, gravitational potential energy at 0.3, spring potential energy at 0.3. Man, it is a really good thing that I'm using a pencil today. Okay, go back to our inventory. Now we're talking about 0.2. What's going on here? Well, that's right where the person got to the level of the trampoline. So at that point, do I have kinetic energy? Yes, keeping it. What about gravitational potential energy at that point? There's a couple of ways we could do this. We could either define the point of reference or the frame of reference as this and call this 0 and call this a negative displacement or negative position, or we could refer to, we could call this the 0 point and call this the change in position. All right, either way, you're going to account for the position. So the way I decided to do it is I decided that at 0.2 there is no gravitational potential energy, and since the spring has not been displaced yet, there is no spring energy. All right, over to here. Once that person has gotten to the lowest point that trampoline will allow them to get, for that moment in time, for that instant, there is no kinetic energy because they're not moving. However, they have a displacement from where they were, and the spring is essentially loaded now. It's been displaced, it's been stretched. So we've got 3 terms. Whatever kinetic energy that person had at 0.2 is going to be equal to the potential energy at 0.3 and the spring energy at 0.3. All right, and then now it's just a matter of filling this in. Now, one thing to understand is, now let's see, let's do this first. Okay, the speed at 0.2 is equal to, and that would be the y at position 1, or I'm sorry, position 3, and since we're talking about a spring, that would be spring constant times displacement squared divided by 2. However, let's not forget, since we're defining this as our reference point, whatever distance down that object has moved in terms of potential energy, that's also the displacement of the spring. So the nice thing about that is that the potential, the position in terms of gravitational potential energy is going to be equal to the displacement as far as the spring is concerned. So I can rewrite this, or just make those slight changes. The kinetic energy at 0.2 is equal to the gravitational potential energy at point 3 and whatever spring energy there is at point 3. Remembering that the displacement for the potential energy and the displacement of that spring are going to be the same. Again, I know that you don't like fractions. A lot of you don't. So I'm going to go ahead and get rid of those fractions now. So I end up with this expression here. And what I notice here is that I have powers of different terms of y over on this side. So I got to rely on my math. I see a quadratic happening, and so what I'm going to do is I'm going to rearrange this in terms of the quadratic. Where that constant there, that part there, is going to be equal to A in my quadratic formula. Okay, this segment here is going to be equal to B in my quadratic formula, and then this whole term is going to be equal to C in my quadratic formula. And then it's just a matter of plug and chuck into your quadratic formula. All right. I'm going to stop it there. If you have any questions, please tweet or email me, and or see me in class, and we'll try to get them ironed out.